Okay, we are looking at problem L in the Unit 1 problem set 3, more spectrometry and spectroscopy. So let's dive in here. So here, what we want to do, first just look at the molecular formula. I'm going to walk you through the steps of how we're solving these problems. This is going to be really reminiscent of something you're going to do on the quiz on Monday. So the first step is you're going to look at the molecular formula and you're going to go ahead and calculate the double bond equivalence. Okay, double bond equivalence is the number of carbons, in this case 10. You always add +1, minus the number of hydrogens over 2, in this case it's 12 over 2, minus the number of any X, this would be halides, any of those, okay, bromide, fluoride. In this case we have 0, minus the number of nitrogens over 2, okay, here we have 0 as well. So now what we have is 11 minus 6. That gives us 5. What the heck does 5 mean? I want to say this because I saw a couple questions in my office hours about this. So double bond equivalence, when you have, let's say you just have one, okay? This can be a double bond or a ring. Okay, the double bond, like I said, is C plus 1 minus H over 2 minus X over 2 minus N over 2. Oxygens and sulfur, you don't count. And that's mainly because they create a one-to-one bond with a hydrogen. So double bonds, for example, this one has 1. Or it can be a ring. So, for example, here, cyclohexane, we have 1, okay? In this case, this would give us an answer of 2. And you can go through and calculate this yourself. Here's one that's really important. This benzene ring. How many do we have here? We have 4. We have 3 double bonds and then three double bonds in 1 ring. And then obviously another one that is fantastic and helps us a lot is this carbonyl, and this is 1. Again, there's a double bond. So if we're good on that, I want to move right back to the problem set that we're on. Whoops, I think it's this one. Right away, we can already gain some information about this. Part of why I'm making this video is because I want to show you how we're going to jump around between these 4 spectra. In the last video, I talked about mass spec, IR, and NMR, and how I mentioned how we're going to jump around. There's not a one-size-fits-all when you're solving these things. Here, right away, we have 5. Anytime you have something that's over 4, you want to be looking for a benzene ring, okay? So let's look here, just real quick. We can decide very quickly if we have a benzene ring. There's 2 major indicators right here in the NMR. This is the proton NMR. How do I know it's proton NMR? That's because it typically goes from 0 to up to about 12. In this case, it's just 8. How do I know this is, and then we'll look over here at the carbon, this one on the bottom. Look at this range. This range is indicative of an aromatic ring. How do I know this is a carbon NMR? It's going from 0 to 200. So if you don't know that already, you can quickly look at your appendix. And the proton NMR, this is still drawn on from my last video I made for you, but you can see here that we know that the aromatic region is around 7, okay? And this varies based on the electronics of the ring. You can do the same for the carbon NMR. Here we've got carbon NMR for the aromatic region. This has a pretty broad range, but anywhere around 120, 140, most likely going to be aromatic, okay? And that's what we have here. Okay, so I already know this piece. As soon as you decide that you know a piece of this compound, I want you to draw it. That's going to help you kind of keep things straight. I already know that I have a benzene ring. I have no idea what's attached to the benzene ring. We didn't dive in yet. Now, this takes care of 4 of for my DBE. This takes care of 4 of those units. Okay, well, what about the 5th one? In this case, you could go stepwise, go through the NMR, and then scroll down and go through the IR. Screw that. Go right to the IR. You know why I think that? Look at this. We've got 2 oxygens. I have 1 more double bond, okay? I have one more double bond. I want to know if there's a carbonyl. What's the fastest way to find out if you have a carbonyl in your compound? Check out the IR. What are we looking for? We're looking for the peak at 1700, around that region. What do we have? Bam. What's that? A little higher than 17? It's like 1720. It's really hard to see. Typically, I will have this listed as to what the frequency of that is. This screams, look at that. We just figured out two pieces of this compound. We know we have a benzene ring, and we also know that we have a carbonyl somewhere. This is super helpful, okay? Now let's dive in to the pieces separately, okay? While I do this, I will be talking more in depth about splitting. I will also be talking more in depth about where in the NMR, we're just talking about NMR right now, but splitting, and then where in the NMR these signals are going to take place, because these are really going to help us determine what is going on. What I would do with this, I'm going to zoom into this proton NMR. What I like to do is I like to make a little table. This is kind of a fail-safe. It keeps me in check, okay? So the first part of the table, I'm going to have the parts per million. These are parts per million. I'm going to list them. Eventually, you won't have to make a table, but this is a really great way. Can I not speak today? Really great way to keep your work in check. So I'm just going to list them from lowest to highest. These are actually listed here already, which is fantastic. Makes it even easier. 2.05, 5.87, and then we have 7.30, okay? Now what I'm going to do is I'm going to list the number of protons for each one. In this case, we're really lucky. Remember in the last video, I said you got to watch out. Make sure that if it says you have 12 hydrogens, that the proton NMR is adding up to 12 hydrogens. Otherwise, you're going to have to multiply that ratio by some number to get that total of hydrogens. Again, this is where we're integrating. It's the area under that peak that number of protons is coming from. Okay, number of protons. Let's look here. If I look, it's listed 3, 1, and 5. 6 plus 1 is 7, plus 5 is 12. We're good. Okay, we have this. Now what I want to do, though, is I also want to list, I'm going to put the number of neighbors, okay? I don't know this right now, but I will. I also don't know this right now, but I do know, what I do know is the splitting. We know what they look like, but we need to figure out if it is split, what does that mean for what that fragment looks like, okay? So now we're just going to fill this in. So now for the top one, we've got a doublet. I'm just going to write a D. The next one, we've got a singlet, a quartet, and then we have a multiplet. I didn't find a lot of discussion on splitting and then comparing that with the n+1 rule. So I'm going to jump over to a blank piece of paper and just kind of walk you guys through what does it mean with the splitting and all that. And in our heads, I would like for us to keep in mind this. We can just do this with this doublet. So kind of keep this D doublet in your mind, okay? It's a signal. This is one signal. D corresponds to, 3 hydrogens. And we're going to figure out what does that mean when it is a doublet? And what does the n+1 rule mean with all of this? And I think this is going to answer a lot of the questions I'm seeing. So we're going to jump over here real quick. So I've already talked about DBE. The next one we're going to talk about is the n+1 rule. So let's take something really simple. Let's just take an alkyl bromide. I'm going to look at these 2 protons here. I'm going to draw them in blue. And we're going to look at what the splitting we expect to be. We can kind of do the same thing that we did with our little table, okay? We have the number of protons. That's an H. We have 2 protons, okay? Now we're going to look at the neighbors. We already know what this compound looks like, so I'm going backwards right now. How many neighbors do these blue protons have? Well, when I say neighbors, what you do is you have to count this way. So here's our hydrogen. This is the carbon that it's on. What you do is you count one carbon over and you ask yourself, are there any hydrogens on this carbon? In this case, there are 2 hydrogens on this carbon. I go back to this carbon here. If I go to the right, there's a bromine. There are no hydrogens on that bromine, right? So again, when you're looking at neighbors, you go to the carbon that the hydrogen you're looking at is on, right? We are looking at this one. We're saying, okay, hydrogen, what do you see? Go one carbon over. This carbon does have hydrogens. It has 2, in fact, okay? Now, one thing to note, we've already been able to determine this looking at this compound quickly. We should just go over this real quick. How many different sets of hydrogens will be on this alkyl bromide? Well, there's no symmetry for this compound, okay? There will be 1, 2, 3 different sets. So there'll be 3 different signals. This is really important that you understand how to, and it was in the second problem set, how do you look at a compound and decide how many signals it has? Keep in mind that when you start to do this N+1 and looking at the number of neighbors, this is dependent upon these 2 hydrogens that are circled in red being the same, as in being equivalent, okay? So, how many neighbors do the blue protons have? They see the 2 red protons. That means In is equal to 2, okay? So number of neighbors over here will be 2, and we're looking at the blue protons. So what is the N+1 rule? If you have no neighbors, you are going to have a singlet, okay? Oop. And we're going to describe the signal. If you have 0 neighbors, N+1 is 1. That's a singlet. If you have 1 neighbor, N+1 is 2, right? 1 + 1 is 2. This will be a doublet. That makes sense. Double, right? 2. If you have 2 neighbors, that means 3. This will be a triplet. That makes sense. Triple, triplet, triplets, right? 3. If you have N is 3, 3 + 1. You're going to have a quartet. You see how this is going? Let's jump over to the blue hydrogens that we just looked at. We have 2 neighbors. That means our N+1 is going to be 3. What does that mean? What kind of signal are we going to get? This will be a triplet. What does a triplet look like? It's a 1 to 2 to 1 ratio, okay? So this is super important because not only do we know we have 3 different signals, we know one of them is a triplet. This is what we're going to be using on the example that we have. I could go through here and walk through the rest of it, but I'm not going to. I just wanted to highlight this N+1 rule. Again, the 2 hydrogens you're looking at, these red ones, are equivalent. So they split the blue hydrogens the same. Okay, so here's our example. Right now, let's look at the red, what I have drawn in red. We have the splitting that I just talked about. We've got a doublet, a singlet, a quartet, a multiplet. What does that mean for the number of neighbors? Well, we can figure that out, right? We know that for a doublet, the N+1 must be 2, right? For a doublet. For a singlet, it would be 1. We can backtrack now. I know the number of neighbors for an N+1 has to be 1. 1 + 1 is 2. N+1, if it equals 1, that means N equals 0. That means this thing at 2.05 doesn't have any neighbors. That's really important. There are 3 hydrogens without any neighbors. I hope your brain is starting to go, I know exactly what fragment that is. Let's look at the quartet. This means that N+1 equaled 4. That means N must be 3, okay? This multiplet, we're not going to worry about right now. You're going to see quickly what it is, all right? Just know that it's too difficult for us to analyze like what's going on with this mess. Let's look at the fragments. Let's see if we can guess any more fragments. We've already guessed that we have a benzene ring. We don't know what all is attached to it. We've already guessed that we've got a carbonyl. But as you can see here, that only accounts for 7 carbons. We still have 3 carbons we haven't accounted for, and another oxygen. Let's see if we can do any of this. Right away, I want you to look at the number of hydrogens, okay? If you look at the number of hydrogens, this is going to help you some. This 1.52 has 3 hydrogens. In order for 3 hydrogens to be equivalent, what would that fragment have to be? You're right, it'd have to be a CH3. And it's going to be bound to, well, how do I know what it's bound to? Well, how many neighbors does it have? It has 1 neighbor. That CH3 is bound to a carbon with 1 hydrogen. What else is that carbon bound to? I don't know. But what I do know is that this carbon here must have 2 things that are not H's. They are not hydrogens because it only has 1 neighbor. So let's go to the next fragment at 2.05. We have 3 hydrogens. That's how many hydrogens are in that signal. That should clue us into what this is. It has 0 neighbors. That must mean that this is a CH3 bound to something that does not have any hydrogens. All right, let's move to the next one. 5.87. It signifies 1 hydrogen in this molecule. 1 hydrogen. Well, that must be a CH, and it has 3 neighbors. Hey, that's pretty cool because right up here, this 1.52 has a neighbor with just 1 hydrogen. So these 2 are most likely bound together. So here's our CH. It doesn't have any more hydrogens. Why do I know that? Because it says there's only 1 hydrogen for that signal. So these 2 fragments here are coupling with each other. We have a CH3 and then we have a CH. All right, let's move on to the next one, the multiplet. The multiplet here just means that these 5 hydrogens, their signals are overlapping, and it's really hard for us to see what it's splitting to and how many neighbors it has. However, we know that we have a benzene ring in this compound, right? Well, this would make sense that these hydrogens would come from the benzene ring. And why else do I know that? Well, like we talked about, this ppm shift is in the aromatic region. All right, so this benzene has something attached to it. We're not really sure. One thing we haven't accounted for, one thing I would look at here, how many carbons have we accounted for so far? Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 carbons altogether. What are we missing? What are we missing? Well, we're missing our carbonyl, which makes sense because it doesn't have any hydrogens attached to it. We have now identified the fragments that we have. There's one thing we are missing though, and it is this extra oxygen here. Okay, so we have carbonyl. We also have an oxygen somewhere. Well, let's figure this out. Let's figure out how we're going to combine these together. Let me move this up real quick. All right. We're going to move this up. Now what we're going to do is we're going to label this NMR. And this is more of what you'll be doing on the quiz. Once you kind of have your work kind of figured out, now you can go ahead and go in and label. So at 1.52, we know we have a CH3 group. It's bound to a carbon with a hydrogen. We know the other 2 things attached to that. It's neighboring CH group. They are not hydrogens. C is a CH3 group. But we know that this CH3 is bound to something without any other hydrogens. And we know that because it has no neighbors. Okay, what's the next signal? We've got 5.87. We know that this is a CH, but we already know that it's a quartet. And we can confirm this. Look at this. Look at that quartet. It's beautiful. So this is talking about this CH. We know it's bound to a CH3, and we're not really sure what else it's bound to. And then our multiplet here, we know, is our benzene ring. Okay, hopefully you're with me now. Now we need to figure out how do these attach, okay? We still have a carbonyl that we're missing because we decided that with the IR. And we're also missing an oxygen here. One of the things you're going to notice is when you look at this spectra. For example, C and D are both alkyl. They are both saturated CH bonds. How come C is shifted further downfield? Well, this is because it's bound to something electron withdrawing, and we talked about that in the last video. Electron withdrawing. All right, what do we have that's electron withdrawing? Well, we have a carbonyl and we also have an oxygen. So you could imagine one of those could be bound there. What about this guy, B? Look at B. B is shifted very far downfield. I would imagine that B has, that this carbon this carbon attached to B, this HB, has 2 electron withdrawing groups on it. Well, what are our groups that we could attach? Well, we have an attachment here to benzene. You can imagine you have this carbonyl. You also have this oxygen, okay? So what we're going to do is we're going to look at where these take place. Let's jump over to the appendix real quick, see if we can get any information just from our normal table. All right, as we look at this table, let's see if we can find out where the shift would occur if a carbonyl was attached to a carbon with a hydrogen. And that's going to show up right here. Where does it take place? Between 2, that's not really a straight line. It's around between 2 and 3 ppm. Well, this is very close to our signal at 2.05, right? 2.05. What about when it's bound to an oxygen? Okay, look here. A carbon with a hydrogen that's bound to an oxygen here. Looks like it would happen near 3 ppm. So this would be shifted too far. So what I would say is and a lot of times when you're solving spectra, I should just let you know, when you're walking through it, you won't always know the exact answer right away. You're going to do your best, and then you can check your work because all of the spectra should really line up. Because this signal at C is at around 2, we are going to put this carbonyl right here. So this gets rid of this carbonyl as something we need to have it bound to. Well, maybe we can get more information about this carbonyl using the carbon NMR. We know this is a carbon NMR, remember, because it's going to go from about 0 to 200, all right? So let's look at this. Where's our carbonyl peak? Let's just dive in just a little bit. Remember that this is TMS. This is used to calibrate the NMR. Here we've got an alkyl. We've got 2 sp3 carbons. Here's another sp3 carbon. What about this guy? What is this? If you're not sure, what you can do, you'll see this often, and some of you already know this by now. Whoops. But you can use your appendix again. Let's scroll down to common solvents. Oh, I already circled it for you. I'm showing another student. So here you've got chloroform. Chloroform is a really common solvent. We use a deuterated version, so CdCl3. The reason we use deuterated solvents is so that way the hydrogens from the solvent don't show up in our proton NMR. And so here we have in the carbon NMR for chloroform, we have 77. We've got these 3 signals. Let's just make sure. And that is in fact the case, okay? So that's chloroform. So we're not going to use that for our determination here. Let's look at this. Where would a carbonyl take place? You got it. Here around the higher region. This is our aromatic region. sp2. These are actually all of our sp3 C carbons. So here, 170. Let's figure out what kind of carbonyl that is. Let's see if we can get any more information. You look at the appendix, it gives you a shift range for carbonyls. And if we look at this, if it were a ketone, you would expect it between 180 and 220. Well, this one's only at 170. Well, what else here is at 170? We have, well, look at this. We have an ester. This is indicative of an ester carbonyl based on the shift of that carbon. So we're going to say that this guy is actually an ester. Okay, this is super helpful, right? We're kind of confused about where we put this oxygen. So you can imagine that it's going to be here. Well, that's interesting. We're kind of thinking that this HB has to be connected to a very electron withdrawing atom, which would be the oxygen. And that would put that carbonyl in this piece here. You see how these two kind of work together here? We know that this oxygen is now part of an ester, and the only other part that would be part of an ester would be in this fragment. See how we're kind of connecting them? What do we have left? Good question. Well, we have our benzene ring. So right now we're kind of thinking this might be the structure. There's a few ways that we can check this. I want to look at the shift of HB and I want to confirm this. Now, for a quiz or an exam, you might not have to do this. However, it's useful for us to be able to walk through. How do you calculate the relative shift of that hydrogen? We're going to use the Murphy-Morrison additive constants. I'm going to show you how to do this. You look at, in our case, we're looking at a CH group, okay? It's bound to a CH3. We think it's bound to an O, bound to a carbonyl, so this ester here, and we think that this is bound to a benzene ring. So we are looking at this hydrogen in particular. This hydrogen is a methine, it's a CH. This is going to tell us what constant to start with. And then we're going to add the alpha shifts. Why do I know it's an alpha shift? We're going to use these alpha shifts. It's because this CH group that we are looking at, we're looking at what is directly bound to the carbon, okay? You can get a beta shift based on one more carbon away, but we're looking at what's directly attached to it. And as you can also see, these numbers tend to be, their absolute value is greater than the absolute value of the beta shifts. So anyway, let's look at this. We're going to start with 1.55. So let's look at this ester, okay? Bound through the oxygen. That would be this guy, and it's alkyl. Perfect, because we have a CH3 group. For the methine, it would be 3.45. Okay, let's look at the benzene ring. Here it is. Here's an aromatic ring, 1.35. Let's see what this gives us. 15. This would be 10, 13, 1, 2, 3, 4, 5, 6, 6.35. This is a little higher than we expect, right? Because we've got this at 5.87. But something I talked about, I wonder if we can find this in this graph. Let me look real quick. No. CH3s are slightly electron donating, and so this would make sense that this would shift it down. So based on what we've done so far, I think that we have our structure. Counter for this one. Let's go through the mass spec. Let's just confirm, okay? So right now, this is what we think our structure is. Actually, what we should do is label it, just like we have here. What is it? DCBA. All right. So we've got D, we have C, we have B, and then A are these hydrogens here, okay? This is what we're really thinking that this might be. Let's see if this makes sense. Molecular formula of 164. This is our mass, this is our molecular ion peak. Quick question, what is this little thing? Do you guys know what that is? Can you explain it? It's from the carbon-13 signal. How much abundance does carbon-13 have? That's why that signal is so small. Here you can see that none of these are labeled. If on an exam I want you to give me a fragmentation pattern to show those, I will list the mass of that, the M over Z for that peak, so that you would know that I want you to draw a fragmentation. Here we've got 43. Let's do this one then. All right, well, let's look at the compound here. We know that alpha fragmentation at a carbonyl is very common, a very common pattern here. So let's look at this. I'm actually going to flip this over here. So the first step would be to lose an electron. You will need to show this I want you to show this in your exams. So let me show it here. Minus an electron, okay? And now what's going to happen? We know we can do alpha cleavage. This is going to give us our psyllium ion. Okay, and then this is also going to give us a neutral radical here. How big is this guy? Let's just look. We know oxygen 16, there's a carbon here, that's 12, and then we have another carbon plus 3 hydrogens, that would be 15. It's 43. Hey, we got it. This has a charge of +1, mass over charge, 43. So this peak here on a quiz or an exam, you would simply just draw your corresponding psyllium ion. I hope that this makes sense. We've now confirmed. You can now walk backwards and make sure that what you drew is indeed correct. Couple things I would suggest. Number one, on the compound that you've drawn, count your carbons, hydrogens, oxygens, all the things. Make sure the molecular formula is in fact the product that you drew. That's one way to check your answer. The second way is going through each of the spectrum and just making sure that it makes sense what you have drawn together, right? Again, we've walked through everything separately. We've even talked about how the carbon NMR was fantastic in helping us understand this was an ester and not, say, for example, a ketone. Make sure that your IR, you have this labeled. In this case, we would want to write down that we have our CH stretches here. Okay? Again, on the quizzes, I will have listed the table of the stretches. Again, fingerprint region, I don't expect you to tell me, although, what's this one? You guys can figure that one out. Okay, so that's it.